So today we are going to pick up and really start getting into StatMech. And the way we are going to do it is to do a little bit of thermo as we get into StatMech, and we will keep doing some thermo on the fly as we go further. But we want to make sure that we understand something really crucial, which is this concept of an isolated system. An isolated system is a construct, right? It's a thought experiment. You can never really make an isolated system. If you see it, it's probably not isolated. Why is it not isolated if you see it? Go ahead. Also photons, right? Something's going on. The black body radiation, for example, something is going on. So it's interacting, right? So isolated system is an ideal construct. It's not going to exist, but it turns out that it is the most powerful way to set up a lot of things. And in StatMech, you will be seeing that we will start with an isolated system and everything else will basically come across. Another math thing that you guys did not mention, no one mentioned in the first class, was Taylor series. Everything will come out as a Taylor series on an isolated system. And that's kind of the beauty of StatMech. But we have seen isolated system in thermo also before, right? So how do we define an isolated system? An isolated system is generally you draw a box. Let's say this is some box. And you say that this box is completely insulated. It's insulated, so no material can pass inside or outside it, no energy can go inside or outside it, and it cannot change its shape or size, okay? So what can you say about such a system? Let's say, and we are doing a thought experiment, right? So the only isolated system we suspect might truly exist is the universe. And even that, we don't really know whether it's isolated or right. So it's a purely idealized construct, but it's very helpful. So for an isolated system, we can say that it is the number. So you know there is something inside the isolated system, right? Maybe it's empty. Maybe it's complete vacuum. But in any case, what can you say about the number of particles inside the isolated system? Is it going to change? You might be having a chemical reaction. Would a chemical reaction inside the isolated system change the number of particles? Why not? This is a PChem question.
Because the chemical reaction is just rearranging.
It's just rearranging atoms, right? If you have fission or fusion, something like that going on, that's another story. But most likely, the number of particles is going to be constant. How about the volume of the system? That is also constant, right? And the energy of the system is constant. So, and together, these three define the macroscopic state of an isolated system. And in 684, many of you took it. One of the starting points is that an equilibrium state of a system can be characterized by three variables. If it is isolated, it can be characterized using NVNE. Okay, so this is an isolated system. Another way of, and so this is our system right over here. Another way of thinking about a system, how to construct when it is isolated. And we will see this construction again and again. Now let's imagine it's the same system, but let's do something. Let's assume that its boundaries are permeable, okay? Permeable in a way that it can exchange heat, mass, volume, all those things with its environment. It's no longer an isolated system, right? But how do we make an isolated system all of this? What we say is, well, you have the system and you have the environment with which it is doing all this business of exchanging things. How about we consider both of these things together? Now, environment is generally going to be much bigger than the system, right? Another term we will keep using for the environment again and again is a bath. It has nothing to do with the bathtub in the bathroom. It's just called a bath, okay? It's a heat bath of a sort. So now if you think about system plus, or a third term that we use for environment is surroundings. So system plus surrounding is an isolated system. And then we can again draw this red hatched line to show this is some sort of isolated system. Okay, so in thermo, we start with this isolated system, and that is what we will do in StatMech also. So what does thermo say about such an isolated system? last time I asked all of you, what is the one certainty in life, right? And you had some creative answers. One of you said death. One of you said, I said time. I think you in front said taxes, or you said taxes. I mean, taxes are sort of thermodynamic, right? It's like heat. You can give taxes to the environment. You rarely get taxes back from the environment, unless in my first year PhD, it used to feel like I get taxes back from the environment because you get a tax refund, right? End of the year, you have overpaid. So it looks like the government is paying you money, but it never really works that way, right? So what we can say about such an isolated system that, so thermo, and if you have read, who here knows the book by Callan? If you have done 684, I really hope you have been through Callan a little bit, right? So, or even otherwise, if you have done the physics undergrad, you have probably seen Callan or even chemistry. So thermo, the key postulate in thermo, which is equivalent to the second law of thermodynamics. So it's kind of funny that I like to think about thermo starting from the second law of thermodynamics, and first law kind of comes later. And we talked about it last time also. Let me write it down again, that there exists a state function. So what do I mean by state function? This is a function that depends only on the macroscopic state of the system, right? There is a state function S, which depends only on NVE, which is thermodynamically complete. It means you can calculate all thermodynamic quantities out of the state function, whatever you need. And that is, a lot of thermo is really just doing those manipulations. Is there anyone who would like to claim that they remember the Maxwell relations, all four of them? Anyone? No one? I buy you a beer or a coffee if you remember all of them by heart. But you remember what they are, right? Is there anyone who does not know? And I'm not talking about the physics Maxwell relations, by the way. I'm talking about thermodynamics Maxwell relations. Is there anyone who does not know what are Maxwell relations in thermodynamics? I hope not. Really, we will be using them a lot. And they are, that's one thing you should definitely put on your cheat sheet, right? It's hard to remember. There are mnemonics where you can draw arrows and remember what you think. So, but those are all manipulations which allow you to go from a thermodynamically complete state function to get all sorts of other things, right? So for an isolated system, there exists a state function S of NVE, which increases, and I will now use the language Chandler uses in first chapter. So it's important that you go through first chapter of Chandler. Chandler really wrote the first chapter of this book inspired by Callan. He was really very much inspired by that treatment, which increases in absence of internal constraints. So again, let's imagine our box, right? We have this box, which is isolated. So it is constant NVE. We know there exists a state function of in this, which keeps increasing if you remove internal constraints. What does internal constraint means? It means that if you put a partition in the middle, part 1 and part 2, and notice one thing, thermodynamics doesn't really care about molecules or atoms that they exist. And right now, all of you would find it very hard if I told you to believe in a world which was not made up of atoms, right? We take it as second nature. Of course, there are atoms. Have you seen an atom though? Has anyone here seen an atom? How have you seen an atom? Not MD simulations. Electron microscope. Has anyone used an electron microscope? Who is working with Forkas and Amy Mullen? You're going to see an atom sooner or later, or with Leah Dodson, right? You will see an atom. I mean, in my grad school, I did an electron microscopy class in my first year. I was not very good in operating microscope. It was kind of crazy. You can see things in atomic resolution, right? But until 1920s, 1930s, no one had seen things like that, right? I mean, think about it. People did not take the existence of an atomic picture or a microscopic or a molecular picture to be for granted. There was a lot of resistance. People thought it's all made up of fluids, right? It's the ether. And it really took Einstein and Planck and all those things to come in 1920s. Our view about how the world is completely changed. And Millikan did his oil drop experiment and he really measured the value of E by M. And it's crazy that people did things like this 100 years ago. It's just mind-boggling. So for this internal partition, we don't have to think about atoms. It could very well be a fluid, right? The point being that, let's imagine that you have a box. In this box, you made a partition. And now you remove the partition. If it had atoms, what would you expect to happen? You would expect that atoms in part one, some of them will go to part two, right? Some of them will come to part one, and it'll kind of mix together, right? And now if you put a partition back, it's not just going to unmix, it will stay the way it is, right? And the same thing can apply to, you don't even have two atoms, it was a fluid, just imagine it's some two kinds of liquids mixed in the box, right? That would be the same thing. If you have partition, you remove the partition, they will mix together, right? And as things mix together, they attain a state from which they don't want to come back, right? That is the whole philosophical thing here. It's like you pay taxes, you're not going to get it back. You die, you're probably not going to be reborn. Time moves in one direction, you're not going to turn it back, right? So it's as simple as that. And it's really almost philosophical. It says that S of NVE is more than equal to S of NVE in the presence of internal constraints, okay? And this, even if you have taken 684, it's been a couple of months, you might find this to be a bit like, wait, I remember reading that, now I don't remember anymore. In that case, I will point out the section in Chandler. Chandler section 1.3 has variational statement of the second law. That's what he talks about, okay? So this is second law of thermodynamics as per Callan, as per Chandler. Now this S function, it depends on NVE. It has two more interesting properties, which we cannot prove this, right? Just like you cannot prove that time is moving only in one direction. You can try, but you won't be able to prove it. It's just something we have observed, right? So this thing is an observation. It's an axiom. It's, and you don't prove axioms. You can try, but you really cannot. There are two more axioms related to entropy. And then when I teach 684, I give some intuition into them. I'm not going to go into that right now. These two axioms are as follows. If you change the entropy, if you change the internal energy of the system, keeping constant number and volume, the entropy is going to go up, okay? Similarly, if you do partial S by partial V at constant NE, entropy is going to go up. These two are also postulates. By the way, if you're interested in these postulates, you can go to my webpage, just like 687. If you type 684, it will take you to the page for 684. And all my lectures from 2 semesters ago are there online. And if you see here, lectures 1, 2, Callan's postulate, there exists equivalence. So if you are interested in studying more, you can go through this. You can look at my terrible handwriting and work through everything there. I asked the same question every time. What is your favorite equation? You can see, kind of repeatable. And I talk about those postulates here also. Oh, I also talk about types of fun. I forgot to tell you all that. Does anyone here know about the 3 types of fun? No? Go ahead.
Type 1 is fun. Type 2 is you hate it and then you have fun.
Yeah.
And then type 3 is you never have fun.
Do you have example of type 3 fun?
A clash, maybe this one.
Horrible, you're horrible. And no, it's like, I used to do a lot of hiking. So type 1 is going on a nice hike, the weather is great, you're stopping for snacks, having a drink. Type 2 is like post-holing, there is a bit of snow, you're sinking, your legs are getting wet, but when you come back, you're like, oh, that was awesome. And type 3 is just like horrible, right? You cannot see, you're totally drenched. Type 3 builds character, but you probably don't want to do it again, right? So I hope this class is somewhere around type 2 fun, okay? Type 1, generally you don't learn things in type 1 fun. Type 1 fun means that you're not really, you need to experience a little bit of stress, right? In order to learn things. So, and I will periodically check with you all whether it's becoming type 3 fun or whether it is becoming type 1 fun, okay? So the right answer is this class is type 2 fun, okay? If you say type 3, then I will have to stop everything. And if you say type 1, then I have to make things harder, okay? So later, just in a bit, we will see that this thing is related to temperature, partial S by partial E. And partial S by partial V is related to the entropy being extensive. If you double, so this property means, and this will become really important, I think in today's class itself, entropy is extensive. This state function depends on NVE. And furthermore, if you increase the volume of the system, the entropy will double. If you double the volume of the system, the entropy will double, okay? And if you go through my notes for 684, I give some intuition into why these might happen, but you cannot really prove these. These are just postulates which you take for granted. I want to focus on the first one, partial S by partial E at constant NV is more than 0. So let's say I draw S function of E. In the bottom here. What should, and at constant N and V. Is this possible? Given what I wrote above, the black curve, is it possible? Why not?
Because the derivative is.
It's positive, right? It's the derivative is positive. In this case, it is going down, right? So the entropy must go up. Okay, so this is not possible. Let's do one more. How about this green one? Is this possible as per this postulate? And how about this orange one? Both are possible as per these postulates. But as per this variational statement, only one of these two is possible.
Yeah, the orange one,
Why?
because if you write it in terms of the other one, and you solve and you do trade differentiation, it turns out that the curvature has to work.
Yeah, so this variation statement, and again, look up my notes for 684 or Chandler's book, also means that the second derivative of entropy with respect to energy at constant N and volume is negative. Does the green one follow this? In green one, the slope keeps increasing, right? The second derivative is positive. So, and if this sounds abstract, remember in calculus, first derivative being 0 corresponds to things being maximum, minimum, or a saddle point, right? You really have to look at the second derivative to see whether it is a maximum or a minimum or truly a stationary point, right? So since you're saying this is maximized, you should have intuition that it's probably going to be some sort of a second derivative being negative, right? Maximum corresponds to second derivative being negative. So these three things you should remember: partial S by partial E, partial S by partial V, and double derivative of S with respect to energy is negative. These three are, this whole page, you cannot prove anything. These are postulates. It's like given. That's how thermodynamics starts. The amazing thing is, given these postulates, you can derive everything. You can derive phase diagrams, you can do whatever you want. It's incredible. So now I want to focus on this first this partial S by partial E at constant NV more than 0. So we just said that due to this double derivative property, this one is also not possible, the green one, but this is the only thing that is possible. Notice also that I had all two of them go to 0 at 0 energy. The entropy going to 0 at 0 energy. That is known as the third law of thermodynamics. You don't really need to care about it. You know, it kind of connects to quantum mechanics that a system has only one ground state. If a system has more than one ground state, it won't be 0, it will be some finite number. So I don't really care about whether this goes to 0 or not. What I care more about is the curvature that it takes. And the correct curvature is the orange one. So let me number my pages and let's draw that one over here. By the way, if I turn pages too fast or anything, just stop me, okay? Don't be shy. So let's draw this. S, huh?
Green one, experiments.
If you see green in the experiment, then your system is not in thermodynamic limit. You have, every time you have a violation of thermodynamics, your N is finite without fail, or your V is finite, okay? So in experiments, yes, you can see that in condensed matter systems and Ising spains and things like that, you know, but it's because the number of degrees of freedom is finite. If you have infinite degrees of freedom, there is no violation. A violation of that would be equivalent to time going backwards. Wouldn't that be wonderful? We could have Obama again for president. So in this case, and almost invariably S looks something like this. I don't know what this looks, what is an example of a function that has this behavior? Can you think of a mathematical function? Log. So there is already a reason why Boltzmann formula was S is equal to K log W, and not log some other function, right? Log has that property. You can already kind of start to see why did the law come, and we will look into that a little bit more. So for this one, S is monotonic in E, right? Monotonically increasing in E. What this means is that any given value of S, there will be a unique value of E, right? If the curve instead looked like something like this, then that won't be true. Any given value of S could correspond to more than one value of E, right? But clearly that is not the case. S follows something like this. So it means S is monotonic in E, which means S and E have unique pair of values at constant N and V. Okay? Everyone fine with this? Okay. What does this mean? This means something quite interesting. If you have S of NVE as a thermodynamically complete state function, you can swap out the S and replace it with E. And if you keep N and V constant, if you're willing to write down a function as a function of N and V, you're not changing that for the same value of N and V, you can swap these out. You can replace S with E and E with S and come up with another state function, E, which depends on NVS. And these two will be not capturing any new information thermodynamically. They have both the same amount of information. Now, the first one was describing an isolated system, right? Where there is constant N, constant V, constant E. This one is even more useless. This is defining a system where there is constant N, constant V, and as if time is not going forward, constant entropy, right? So I think there are some examples of how you might be able to construct such a system in experiments, but it's not intuitive. You cannot run a lab experiment where N, V, and S are constant. But if you were to do that, just like S is maximized at equilibrium under constant NVE, similarly, E is minimized under equilibrium at constant NVS. This should not be that unfamiliar to you. Potential energy minimization is something we all have used many times, right? You're all liking to sit down. Why isn't Lewis just jumping up and down? He likes to be in a low potential energy state. You know, if the class went 5 hours longer, they would probably like to lie down, even lower potential energy, something like that, right? So under constant NV and S, the potential energy gets minimized. And these two statements are equivalent. Notice that we have moved from maximized to minimized, and this really happens from this curvature property. Okay? Any questions about this? Yeah, what?
The way S and E are exchanged, we can also exchange S and P because del S by del P.
You can do all sorts of things. You can come up with funky things. You can keep exchanging, and there is a name for it, which is Legendre transforms. You can, each of these is a Legendre transform of everything else. And in Callan doesn't even cover all the exchanges. The only thing you cannot do is to exchange in such, later we will, I don't think we will cover it here, but you could, in your 684, you probably do it sometimes. So right now when you exchange, notice that all three are still extensive, right? So this is not Legendre transform. This is similar. And what your Samyak, right? What Samyak is saying, I could do the same thing. V of E N S. No one is stopping you. It's just even more useless to construct a system where the energy is controlled, entropy is controlled, and number is controlled. You can do it, but it just happens to be not very useful. And you can do further constructions where you remove variables, and instead of extensive variables, you have internal intensive variables, and that becomes a Legendre transform. What I want to talk about here is, let me go to the next page. So we have S as a function of NVE. If S is a nice function of NVE, then we can write down the total derivative of S, right? What will the total derivative of S look like? It will look like partial S by partial N at constant VE multiplied by Dn plus partial S by partial V at constant NE multiplied by dV plus partial S by partial E at constant NV multiplied by dE. Okay. We could do a similar thing for E of NVS, dE. What should be the first one? Partial of with respect to? Well, any one of them could have been the first one, right? I mean, yeah, but you get the same idea here. It will be Dn. And now what should I hold constant over here? Vs. And in thermodynamics, it's always very useful to write down what is being held constant. That is the origin of so many errors that you can make if you're not careful in what is being held constant. And then we can, not partial S, this will be partial E by partial V at constant NS dV plus partial E by partial S at constant NV ds, right? I think I got it right. So E, NVS, 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 SS, VV, and N. Okay, let's call this equation 1. Let's call this equation 2. Now, turns out this thing is the chemical potential, mu. In 634, you work through this proof as to why is this chemical potential. Intuitively, it makes sense. Chemical potential tells you what happens to the energy of a system as you increase the number of particles in the system, right? Chemical potential is like potential for more chemicals, right? So, and you could generalize this to a multi-component system where N will become N1, N2, N3, N4, something like that, right? Same idea. So mu is the chemical potential. What would you expect energy by volume to be? What thermodynamic quantity should this correspond to?
Negative pressure,
Why?
because when the system expands, it does work on the environment to
Yeah.
expand.
Yeah.
So it loses energy.
Yeah, but also we can do dimensionality analysis and think about it, right? What is the unit of energy? Joule, right? Let's say kilojoule. What is the unit of volume? Meter cube, right? So is that the unit of pressure?
Yes.
What is pressure? Pressure is force over area, right? What is the unit of force?
Times distance. Work divided by distance.
Work is force multiplied by distance, right? So force is work divided by distance, right? And work has the same unit as energy. So force is kilojoule per meter multiplied by 1 by meter square. So this is force and this is 1 over area, right? So it has the right unit as pressure. And you can show that this is not just pressure, but this is minus pressure. And again, if this is rusty, go through my notes, go through Callan, go through your 684 or 481 notes. This is part of the prerequisite of the course. Third one is a bit funky. Anyone remembers what is this third one?
Temperature.
That's temperature, and that is the most accurate definition of temperature. So, you know, next time when it gets colder, you can go and tell your non-physics or non-chemistry roommate, oh, the partial derivative of energy with respect to entropy at constant N and volume seems to be very low today. And like, what are you talking about, right? So temperature is partial E by partial S at constant NV. And this is the most accurate definition of temperature. And right now I could define these as the thermodynamic temperature, the thermodynamic chemical potential, and the thermodynamic pressure with a minus sign. In Callan, I think maybe Chandler also does this as an exercise. You can show that these are similar to what you expect true pressure, true temperature, and true chemical potential to be. Okay. So in other words, now we can take equation 2 and write it as dE is equal to mu dN minus P dV plus TdS. And this is integrated first and second law. In thermo, if you forget all relations, this is one relation you should remember. You should try to remember. From this, you can derive absolutely anything. You can write a similar fundamental relation for entropy also. You can do it for all other functions. Samyak asked me what happens if you did volume. You could write a fundamental relation for volume also. It's just that it might not be that useful. This one is super useful. And you have seen similar forms of it. Let me number it as equation 3, and let me write down equation 3 again on the next page. So equation 3 said dE is equal to mu dN minus P dV plus TdS. Okay, this was equation 3. Let's rearrange it. Let's write it as dE is equal to TdS plus minus P dV plus mu dN. This is the same as writing dE is equal to delta Q plus delta W, or the first law of thermodynamics. Okay, this is first law of thermodynamics. This does not have as much information. Equation 4 has less information than equation 3. Equation 4 does not tell you about the nature of heat, right? Equation 4 does not have any nature of entropy. Equation 4 is, I take this cup of coffee, I do work on it, or I give heat to it, the net effect will be increase in internal energy of the coffee molecules. That is all it is saying, right? Equation 4 is lacking something. Let's take an example of equation 4. Let's say you have an egg here in your hand and you drop it on the floor, right? When you drop it on the floor, what happened? And let's not worry about gravity too much, okay? You just happen to drop the egg on the floor and it broke into many pieces, right? So, or even better than an egg, let's imagine a ball which is bouncing on the floor, right? Every time the ball bounces on the floor, what does the ball do? It had some potential energy. You started from here. It went and bounced on the floor. When it touches the floor, what happens to that potential energy that it went with? It became kinetic energy, right? By the time it got there. What happens to this kinetic energy?
It spreads out.
It spreads out in the form of heat, right? It loses some taxes, right? Some of it is gone. Now it cannot bounce back that much up. It bounces a little bit less. Goes again, gives some heat out, comes up again, and keeps doing it again and again. There is a specific class of material known as metallic glasses. You can go and Google its video. They have this highest coefficient of restitution of any material. Though balls made of metallic glasses are super crazy. They can keep bouncing for like half an hour. It's mind-boggling. So they try to use it in ball bearings on the rover on Mars because they don't have friction. So they are really, really energy efficient. The problem with them is they are glasses. So when they break all of a sudden, right? So I had friends actually working on that. It was super cool. And I think in some extent they are actually being used on the rover, which is fascinating. So, but the problem with this equation, if you were to write down the negative of this equation, minus dE is equal to minus delta Q minus delta W, it's the same equation, right? I just multiplied everything with a minus sign. So this is like a ball was sitting on the ground, sucked up some heat from the ground, and just bounced back up. Went back, sucked more heat, bounced back up higher. We have never seen that, right? It's not going to happen. First law of thermodynamics does not tell you which of these processes is possible. You need to have second law of thermodynamics for it to happen. Why? Because of these postulates that the entropy of an isolated system must behave a certain way. Okay, so this is the integrated first and second law of thermodynamics, and this is just the first law of thermodynamics. Okay, any questions about this? So we are now ready to go into StatMech. I want to just make one more point. So far we studied S as a function of NVE, such that, actually, let me make a table. I'm going to make a table of control parameters and the corresponding state function for that control parameter, which is either maximized or minimized at equilibrium. Okay. If your control parameters are NVE, what is the state function that is maximized? Entropy, right? If your control parameters are NVS, what is the state function that is minimized? Energy. What if your control parameters are NV and T? Then the thing that is minimized is the Helmholtz free energy, or the Helmholtz energy, which is equal to E minus Ts. And this is a Legendre transform of the entropy. This is a Legendre transform and of entropy. I don't really have time to go into what a Legendre transform. This is something which is covered in 684. If you have forgotten what this is, don't lose heart. It's okay. Just remember the shape of this function, how it looks like. So you had S as a function of NVE, and what you want to do is to come up with a function where E is replaced by something which is intensive, right? And in order to do that, you take E and you subtract out minus partial E by partial S at constant NV S. This is the exact definition of a Legendre transform. Okay, so just for the sake of completeness, and this is equal to E minus Ts, because that's how we defined temperature. If this part is Greek to you, that's okay. Don't worry about it. The thing to remember, actually, my red is a bit too much. No, this part, if it's Greek to you, that's okay. What you should remember is A equal to E minus Ts is the right state function when your experiment is being conducted at constant NVT, not NVE, okay? And what is the example of a chemical, or can you think of a lab setup where NVT are constant? What would that be?
A calorimeter.
Huh?
A calorimeter.
Or a furnace, right? A furnace has fixed volume. You probably made it very well, nothing is escaping, and you're controlling the furnace to be at a certain temperature, right? Or a calorimeter, right? So NVT, you have A, NPT, the corresponding state function is G, which is H minus Ts. NPS, constant number, pressure, and entropy. The state function is enthalpy, which is E plus PV or E minus PV. Anyone remembers? Huh? Sure. Now you would think, yeah, and actually there are situations where NPS are constant. Yeah, in nature also, which is kind of crazy that it happens. So, given what are your control parameters, there are state functions that are minimized or maximized. And this is the main message from thermo, that you have a list of such state functions. You have partial derivatives that give you useful properties. You have double derivatives that give you even more useful properties, Maxwell relations and things like that. And you can manipulate these to get whatever you want. It's super useful to know what are the state functions. And every time you conduct an experiment, you need to think about what is the state function that corresponds to it, and you work with it, okay? In StatMech, we will have something, I want to write down one more, which is constant chemical potential, volume, and temperature. In this case, the state function is the grand potential, which is equal to minus PV. This is one we often tend to forget, the grand potential. Now, notice that in this, there is something very special about this third one. And this one, NPT and MuVT are very different from all the others. Can anyone spot the difference? Apart from the obvious thing, they're different variables.
They have two intensive variables.
They have two intensive variables, right? In NPT, N is extensive, right? When you double the size of the system, well, you double N, so N will double per construction. But pressure does not depend on the system size, right? You talk about 1 Pascal, whether it's some small molecule or whether it's you or whether it's Earth's surface, something like that. Same for temperature, it does not depend on that. MuVT is the same. Chemical potential is intensive, temperature is intensive, volume is extensive. So we have examples here where there are two extensive variables. And we have two examples where there is one extensive variable. For those of you who really like Laurent transform, you should go and try to take one more Laurent transform, and you will not get a state function. You will get 0 equal to 0. You cannot describe a system if all three variables are intensive, because that would just mean that you don't have any information about the size of the system, right? So it's not going to work. So this is kind of where it stops. So, and this is a table that you should write down somewhere. We will be revisiting this table again and again and again. We will add a third column to this table, which will be the StatMech ensemble corresponding to things. Right now, we are going to talk about constant NVE and just start from there. Okay, this is the last of thermo I'm going to do. Any questions before we jump into StatMech now for the remaining? Yeah, go ahead.
This might be a slightly stupid question, but what about mu, p, and s?
You can do it. It will be like you should hang out with Samyak. You guys come up with the funkiest state functions and ensembles. You could, no one's stopping you. Do it and think about it, whether it might be useful somebody. You can keep doing things like that. As long as one variable is extensive, you can come up with whatever. As long as at least one variable is extensive. All three can be extensive, but you need to have. And it might be a good question for you to solve, like how many combinations can you come up with? I think there is a finite number of things, right? And you just stop there. So any more questions about thermo? You need to ask me questions. Otherwise, what I'm going to do is to just be like Fatme and ask Fatme a question. No, not right now. It's okay. She's like, ooh, what? No. So please ask me questions, or I promise I will ask you questions. Okay. Now we are really ready to start 687. I made a comment about StatMech last time that equilibrium StatMech is the study of time independent fluctuations. Why time independent? Because it's equilibrium StatMech. You have already reached equilibrium, right? So it's like the point where thermo says nothing is going to happen now because S has been maximized. That's when StatMech kicks in and says, hold on. If I am going away from the thermodynamic limit to finite number of systems, actually there are fluctuations in this system. And they are time independent because you have already reached equilibrium, nothing is changing. And these fluctuations carry a ton of information. And that's what we are going to see what happens, okay? So, and what do I mean by these time independent fluctuations? Let's say we are talking about a topic which is unfortunately very politically controversial now, which is the temperature of the Earth, right? As a function of number of years, right? If you really zoom in, like, let's say you zoom in to temperature over the course of 10 minutes, okay? Let's say your time scale is something like 10 minutes. How do you expect the temperature to look like? Will it be a flat line? Probably not. It'll still be fluctuating, right? And it will look something like this, right? As you increase your, this is like a logarithmic time scale. As from minutes, you go to hours, to days, to decades. You will again see fluctuations, but these are not time-dependent fluctuations, which are much longer. And these are also coming due to external driving forces, okay? So time independent fluctuation means that you're looking at something in the absence of external driving forces. It has reached equilibrium, but things are just going to keep changing on a natural way, right? And it will become clear as we go further. So thermodynamic limit, which is where thermodynamics applies, is once again, n tends to infinity, v tends to infinity, and the ratio, the density is some finite number. Doesn't have to be constant, something could be going on, but it's a finite number. In StatMech, we will really be talking about when n is finite, v is finite. Later, we will be able to take the limit in the infinite value, n tends to infinity, and then derive information about thermodynamics. But practically we will be working with finite number of n and v. So thermodynamics says that macroscopic state of a system at equilibrium can be defined in terms of three variables. And I'm not saying, notice in this table something was common, always three, right? I never used 4 or 2. Why is that the case? Why always 3? What's special about 3? Where is this 3 coming from? Even simpler, 3 is coming from 3 types of equilibrium, right? N corresponds to chemical equilibrium, whether mass is being exchanged or not. V corresponds to mechanical equilibrium, whether the system is changing shape or not. And E corresponds to thermal equilibrium, whether the system is exchanging energy or not. So these 3 variables come from 3 types of equilibrium. Mechanical equilibrium, and I will always write equilibrium as EQBM, leads to terms like V. For example, if the system is isolated mechanically, but if the system is allowed to change volume, then what is the term we get? That is pressure, right? So they are conjugate variables. You cannot control both of them at the same time. You have to pick one, right? Chemical equilibrium. You will either have N or mu. You cannot vary both of them at the same time. And you can generalize this. You can have N1, N2. Similarly, you will have mu1, mu2, things like that. Chemistry does not really happen in a single species system. You're probably going to have more than one species. And the third one is thermal equilibrium. That will be either energy is constant or the temperature is constant. If one of these two is being controlled. Okay, so we have 3 types of equilibrium, either mechanical equilibrium, chemical equilibrium, thermal equilibrium. And depending on whether you are in equilibrium or whether you're not in equilibrium, you will have one value coming from them. Okay, so you can almost see that there is like a menu of options here, right? Why isn't there a 4th type of equilibrium? Can you think of a 4th type of equilibrium? What would it be?
Electrical.
Nah, that's just chemical potential of electrons.
Wait, isn't why would the, oh wait, I guess it does include the,
Yeah.
The energy of the
Yeah.
charge.
How about information equilibrium? Right now, you guys are learning from me. At the end of the semester, I should be learning from you. At least that's what I tell my PhD students. That's what happens around 3rd or 4th year. They start proving me wrong, and that's wonderful. You know? So right now, I mean, you can write down and it's relevant, right? And that's where many of you pointed out thermodynamics as information theory related, but you could totally write down an information equilibrium, whether the system is gaining information or exchanging information or things like that. But in this class, we will be interested in these 3 types of equilibrium, okay? So a macroscopic state of a system is always defined in terms of 3 variables. It could be NVE, it could be NVT. It cannot be all 3 intensive, right? For the reason that then you don't know, you're missing out on some information about number of particles in the system. So 2, at least 1 has to be extensive, 2 can be intensive. That's a macroscopic state. At the same time, now I'm going to introduce a new term, nothing profound, just we have to be careful, which is the microscopic state of a system. So while the macroscopic state of a system had 3 variables, a microscopic state of a system with n particles has 6 n variables. Okay, these 6 n variables correspond to position vectors of each particle let me write it down. Instead of writing x1, y1, z1, x2, y2, z2, I will just write it as r1 to r3n. Okay, this corresponds to position of every particle. And what else? Where did the other 3n come from? The particles are moving, right? Their momentum. We could also have written velocity. It's the same thing. It doesn't really matter unless you're doing quantum mechanics, I guess. But classically, it's basically similar. So a macroscopic state of a system can be denoted in a so a macroscopic state is a point in three-dimensional space. It could be n, v, or e, or it could be mu, or pressure, or temperature. Only thing, be careful, all three cannot be intensive, then you're screwed, okay? One should be extensive. So this is a macroscopic state of a system. This is some other macroscopic state of a system. The microscopic state of a system is a bit hard to draw, right? Because it's a 6n dimensional space, and n is generally huge. What do you think is your n?
Around 20 billion.
Avogadro number, come on, don't give me
Oh.
that. Yeah, you're probably a mole of something, right? Around 10 to the power 23. How many atoms do you think the universe has?
Power 100.
Huh?
To power 100.
Yeah, it's around 10 to the power 50. And when people do drug design, like in my group, the number of drug-like molecules that exist in the universe is around 10 to the power 70. It's more than the number of atoms in the universe because you're just joining things, right? So of course you can be more and more. 2 to the power 100 is approximately correct. So the microscopic state of a system has to be drawn in a very, very high dimensional space, right? So it's going to look something like a vector here, a component here, a component here. One second. Lots and lots of lines, and we cannot really draw it. Let me do it this way. And let's say these things correspond to R1, R2, R3n, and these correspond to P1, P2, P3, P3n, right? So it's a 6n dimensional vector space. 6n dimensional space. This space has a name. This space has a very specific name. It is known as the phase space of a system, okay? So the phase space of a system means that you have written down R1, R2, R3n, P1, P2, P3n, okay? Now you might not care about the momentum. And later we will see why that is the case. Often we don't care about the momentum. It kind of averages out in a boring way. Often we are interested only in R1, R2, R3n. This is a 3n dimensional space, right? The name of this space is configuration space. And these are very specific meanings. Often people call R1, R2, R3n as phase space. That is not true. Phase space, you need to know the momentum also. The third one, analogously, is if you know only about the momentum, P1 to P3n. Well, that has an easy name. That is known as the momentum space. And StatMech really concerns these two, phase space or configuration space. Often we will be talking only about configuration space because momentum kind of, as you will see, turns out to be boring. Often it just follows Maxwell-Boltzmann, and we can write down simple properties about what happens in the momentum space, okay? So I'm not going to be drawing this thing all the time with so many squiggly lines, okay? Or so many coordinates, it's hard. So what I'm going to do is to instead draw axes that look like this. I will just call this one as R and this one as P, okay? With the full intention that R is a vector and P is a vector. R itself has many components, P itself has many components. So now let's consider a system moving in this phase space, okay? You prepared a system. What do I mean by a system? It could be an oxygen molecule, right? How many atoms does an oxygen molecule have? It's 2, right? I mean, don't doubt that. So what is the dimensionality of phase space for oxygen molecule? Two, 4, 6, 8. Why? Who thinks it is 12? What is the number of particles in the oxygen molecule? 2. And how many dimensions are there? 3. We are in XYZ space and the corresponding momentum, right? So 6 plus 6 is equal to 12. So oxygen molecule is moving in a 12-dimensional space. Now, if you really want to be careful, you'll be like, but the bond length is constrained. So that might reduce, we put a constraint on it, right? So now you're moving in 12-dimensional space, but you might be moving on a shell because there is some constraint on it, right? But we will assume that bond length is fluctuating. But so you're not moving everywhere, you're moving in some sort of limited thing. So, but in general, you start at some value in this phase space and you move. Let's say you started at 0.1. When I say you, it could be a molecule, it could be you, it could be anyone else. It moves, let's say it goes to 0.2. And let's say it goes to 0.3, and then it goes back and so forth. And then maybe at some point, it's going to do this. So I'm going to draw an arrow. The arrow went from here to here, to here to here, to here to here. Then it seemed to have crossed itself and come across somewhere else. Can this happen or not? Can trajectories in phase space cross themselves? What would this mean? This means that if you prepared the oxygen molecule, all 12 coordinates, 6 positions and 6 momentum, with the exact same value, you don't know what it's going to do next. Maybe it wants to go get an ice cream. Maybe it wants to go get a burrito. Is this okay? That given exact value in the phase space, given exact value of the positions and the momentum, there are 2 choices. Why should we be very perturbed by this? Or not perturbed? What does this mean? Huh?
It's not deterministic.
It means, yeah, what were you saying? Yeah, so more than that, it is not deterministic. You could create a system with exactly everything same, and you don't know what it's going to do next. That's kind of, I don't know, reassuring in a sense that we have some choice in what we do, right? We might get somewhere, or if life is truly deterministic, that means whatever is going to come out of my mouth next is already written. And maybe it is, who knows, right? We don't know. So this is, so the challenge here is, can trajectories in phase space, can a trajectory in phase space cross itself, recross itself? That is the question, okay? Turns out classical mechanics is indeed deterministic. If you were just working with things classically, it can recross. It cannot recross. So how would classical mechanics look like? In classical mechanics, if you had PNR, you started here, you went like, you came here and you did this. You think you're going to cross, you're going to cross, no, but you'll do this. You can come as close as you wish, but you won't be able to cross, okay? This is in classical mechanics. And this is depressing because this shows that we really don't have any choice. It's all set. The universe was created with a certain value of PNR, and that's it. But we know the world is not classical, right? The world is quantum. Who said Heisenberg uncertainty relation? When I asked, you said. Both, at least 2 of you said. What does Heisenberg's uncertainty relation tell you about this part of the phase space? So that is Rachel, and what's your name? Let me find it. The undergrad is just missing today. She has gone for, that's Julia. Undergrad has gone to grad school interview or something. She works in my group, so I know too much about her. No. What does quantum mechanics tell us about trajectories coming too close to each other? Any idea? Especially Heisenberg. there is a minimum. And what is that minimum? That is Planck's constant, right? So if we had to redo this figure by keeping quantum mechanics in mind, we cannot just draw lines which get infinitely closer. There is a minimum resolution now we have. And that resolution is going to look like a box like this, right? And the size of this box is Planck's constant, h or h cut, whatever you want to call it. As per quantum mechanics, once you enter into this box, so let's say you have a trajectory that started in this box, okay? It started somewhere. Number one, you cannot say where it started in the box, right? Because that's your uncertainty. You cannot do anything. If you try to resolve your x coordinate finer than this one, then your y will blow up, right? Your momentum will blow up. So you cannot be precise in both of them. You're kind of limited within this box. You started somewhere in this box, you moved, and then you came back to this box. As soon as you come back to this box, you no longer know where you are. So quantum mechanics immediately builds in non-determinism because it says once you get into this resolution, you don't know what's going to happen. And quantum mechanics allows for trajectories to recross and do all kinds of funny things. Okay, so quantum mechanics is non-deterministic, which is why, in fact, we use probabilities to describe quantum mechanics, right, and things like that. So
Isn't the evolution of the wave function itself?
yeah, but do you observe the weight function?
No,
You observe the probability psi star.
we don't even observe trajectories.
No, that's the problem. You observe probabilities of trajectories. So quantum mechanics makes this puzzle to be less relevant. It says, no, it's not deterministic. For quantum mechanics, non-determinism is like a part of everything, right? Because we are thinking in terms of probabilities and things like that. So it all just goes away. Quantum mechanics works with wave functions. And then you are really thinking about psi star, which is the probability. And as soon as you introduce probability, it's game over for determinism, right? It's all probabilistic. It's done.
Well, I don't even need quantum mechanics. I can just make the have like a coffee thing. And I put milk in it. I don't know how it's gonna. I cannot tell like how it's gonna expire.
But that is exactly the puzzle I'm trying to say. The thing that you believe with so much confidence that I cannot tell what's going to happen. The point I'm making is, as per classical mechanics, that would not have been the case. Classical mechanics, number one, the other interesting thing here is, in classical mechanics, you could have run this trajectory backward and forward, and both will be allowed. Your coffee could be stirring, your coffee could be unstirring. That goes back to E is equal to Q plus W with a minus sign. Quantum mechanics, no, every time you enter a box, you lose some information. So you cannot just turn it back precisely, right? Because you have lost that information. By the way, if you're interested in this topic, there is a physicist, I think at Stanford, Leonard Susskind. Go check out his videos on YouTube. They're beautiful. He talks about this in great detail. It's like absolutely fantastic. It's totally, you cannot just listen to it on your headphone. You have to see him teach it. And he goes into exactly this topic, including coffee thing and stuff like that. So the point here is, classical mechanics is deterministic. Trajectories can run forward, trajectories run backward, nothing stops you. Quantum mechanics and thermodynamics are fundamentally chaotic. You cannot just run things forward and backward. And part of the reason is this Planck constant. And the reason I also mentioned this is, as we go further in StatMech, you will tend to forget that things are, it's easy to forget in thermodynamics that entropy only increases in isolated systems. Thermodynamics, StatMech, you will see, we will not talk about it more and more. And the more you study StatMech, you will tend to forget that thing more and more. It's only thermodynamics or quantum mechanics which tells you that, nope, there is a preferred direction. This is the direction of chaos. This is the direction of time. So, okay. And there is a related theorem known as Liouville's theorem, which talks about how much volume will a trajectory cover in phase space. Sometimes I do this in 687. This time I'm not going to do it. If you're interested, you can go and look it up, but we are not going to cover that over here. Okay. So now we are at a very interesting point. So what have we done so far? We have talked about macroscopic state of a system, which is made up of 3 degrees of freedom, right? One of them, at least one of them, has to be extensive. Microscopic state is made up of 6 degrees of freedom. Another way, and in this 6 degrees of freedom, if it was classical mechanics, the trajectories are deterministic. If it was quantum mechanics, the trajectories are non-deterministic. There is another way to make classical mechanics non-deterministic, which is remove 1 degree of freedom. From your 600 degrees of freedom, as soon as you remove even 1 degree of freedom, you have lost information, right? And suddenly you have to worry about memory because that degree of freedom screws up everything. And that is a challenge. So that is coming due to loss of memory, right? You don't know what's going to happen. So this is what we have covered so far. Why did we do this? Because thermodynamics, while it talks about macro states, statistical mechanics is all about what is the probability of microstates. That's what we are going to study next. And in order to do that, we again have to go back to our favorite system, which is an isolated system. We will be spending a couple of classes at least with this completely isolated system. This box. Let's draw a 3D box. Oh, that's not a box. Okay, we have a box which is completely isolated. So it has constant NVE, isolated system. I want you to do a thought experiment. Why should you do a thought experiment? Well, Einstein did thought experiments and it served him well, right? So if you do good thought experiments, you might get a Nobel Prize. Thought experiments are very good. Let's do a thought experiment. Let's say we have prepared a system which is completely isolated. Let's imagine this is a box, okay? And it is made up of some molecules. Maybe it is made up of some fluid. I don't know what is inside it. And let's say I shake this box vigorously. I keep shaking it for as long as possible, for years, decades, whatever. What's going to happen to the molecules inside this box? Let's make it more real. Let's say you are all particles, okay? And let's say there is no gravity. And I know that you exist in this room. You don't talk to each other. You are all, which often happens. I mean, during COVID, that's how it used to happen, right? When teaching on Zoom, no one talks to each other. It's terrible. So, and you are in this box, and I shake this box as vigorously as possible. What are you going to do? It will take some time. You are stronger than you believe. You will move around, right? He will move from here to there and everywhere, right? And there is no gravity. Let's not worry about gravity. Okay, you will move everywhere. And in fact, each one of you will move everywhere. If you're ideal, each and every particle in this box will do things like this, right? And the other reason why I pointed out about the trajectory intersecting is because quantum mechanics tells us that's not a problem, right? It will intersect and go everywhere, right? And this is for particle number 1 in black. Particle number 2 will also do things like this. Particle number 3 will also do things like this. Particle number 4 will also do things like this, okay? Now, instead of shaking you, what I'm going to do, because like you, what's your name? Huh? You were not there in the last class, right? No. Okay. Atli. Yes. Okay. So Atli said, I will die if you shake the box too hard. Okay, so let's not do that. But again, you're going to have the same problem. Let's say I observe you for a very, very long time. Again, you will say I'm going to die. Fine, but let's not worry about that, okay? Instead of shaking you for a very long time, if I observed you for a very, 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 very long time, then the behavior would be something like this, right? You're just moving in this box, you go everywhere, you come back, and everyone goes everywhere, right? So I could, now let's say I have some state function or some observable O. And I do this thing where I follow a trajectory for a very, very long time. And I observe this in phase space. And I see what is the value that O is going to take as I study this trajectory for enormous amount of time, okay? So I will see some value O1, I will see some value O2, I will see some value O3, I will see some value O4, so on and so forth, right? So I can write down the time average of this observable. I'm going to use the quantum mechanics notation, the bracket notation from Dirac. I'm going to call it average of O. How will it be mathematically given? It will be given as the observation OI divided by the number of observations, right? So it will be I is equal to 1 to M. Let's say I did M observations and I divide this by M. This is the time average of any observable, okay? This is one way of calculating some state function. And this is kind of what you do in an experiment. Anytime you run an experiment, you calculate some average, right? And you don't just calculate it like this, you run it, equilibrate it long enough, you see it could be any average, right? It could be some sort of chemical property, it could be thermal expansion coefficient, it could be heat capacity, you run it long enough, you make some observations and you make sure that it has sort of average, right? If this thing changes, if you double M, then it has not have converged, right? You're not in equilibrium, it should not change. M should be a very large number. That's one way of observing the system. This is a time average. Another way of observing the system is, and this is going to sound abstract, so make sure to pay attention in the next 2 minutes. If you do not pay attention in the next 2 minutes, it's game over in 687, okay? I cannot emphasize this strongly enough. Okay, so pay attention. If you're awake, if you're asleep, wake up. And this is where looking at all of you will be useful. So we have Didi, we have Artley. Okay, now let's just focus on these two, stare at them, okay? Yes, no problem. Or at Rayal, right? Let's have 3 particles in her, she's not pleased. Let's say we have Rayal, Artley, and Didi. And they don't talk to each other. They should, but at least in the class, thankfully, they don't talk to each other, right? So in the first experiment, what did I do? I just observe Rayal as she is an ideal gas molecule, so she just bounces around everywhere, no problem. You know, I observe her long enough, she goes everywhere, and I compute some ensemble average. And I get some average by calculating this for a very, very long amount of time. I could do the same thing for Didi. I observe him for a very, very long amount of time. I could do the same thing for Atli. I could observe you for a very, very long amount of time, right? Now let's go one step further. Let's imagine all of you in this box, and I observe something that is a function of how all of you are behaving, right? You don't, now we are even removing the restriction that you're ideal. Let's say you're talking to each other. And let's say I make another replica of this classroom. It could be in a parallel universe, it could be whatever it would be, right? And let's say I make thousands of replicas or millions of replicas of this classroom. These replicas, instead of observing one classroom for a very, very long amount of time, if I made many, many copies of the same classroom and observed each of them for a very short amount of time, the 2 averages will be the same. This is not obvious. No one has ever proven this. Okay, so this first average that I talk about, which is to follow one of you for a very long amount of time, this is called an ensemble average, right? A time average. The second one is when you make an ensemble of copies of the same system. Now, how do I make this ensemble? It has to be consistent with what you know thermodynamically about the system, right? It has to be consistent with what you know about the macroscopic state of the system. In this case, we are studying an isolated system. So each copy in this ensemble, normally we use ensemble for music, right? It's the same thing. There are many musicians who are playing something in something like has same NVE. And if you study the average for this ensemble, this will be the same as the time average. And next, we are done with time here. Next time I'll start from the same point. I'll just give you the name of this statement, which seems almost obvious. This is known as the ergodic hypothesis, that time average is equal to ensemble average. No one has proven this. You cannot prove this using the fanciest math. If you prove this, you'll probably win the field battle. I'm not kidding. It's that level of math. It's harder than proving anything in math. I think it's harder than proving the Riemann hypothesis, if you know about this. It's there. It exists. I will also show you some examples next time of chemical systems where it might get violated. And this is what we will talk about next time. So go and look it up, the ergodic hypothesis, and we will meet next Tuesday.